everyone, welcome back to the course on econometric modeling. This is module 17. Module 17 is part of part 3. This deals with multiple regression analysis and several diagnostic tests. So, once we are through with the discussion of multiple regression analysis, after that we discuss the problem of multicollinearity, which is a problem outside the CLRM assumptions, that it does not as such violate any CLRM assumptions. Then we discussed omitted variable and measurement error problems, which actually can lead to unbiased and inconsistent estimators. In the next two modules, we will be discussing the problem of heteroscedasticity. So, module 17 first introduces the problem of heteroscedasticity, how we define it, and what does its presence mean, what kind of problem it actually leads to, and also we talk about detection of heteroscedasticity, that is how we can test for the presence of heteroscedasticity, and in the next module we will talk about how to deal with heteroscedasticity. So, first of all we have already introduced homoscedasticity. So, homoscedasticity means that the actual values of the error terms in the sample will sometimes be positive, sometimes negative, sometimes relatively far from 0, sometimes relatively close, but there will be no a priori reason to anticipate a particular erratic value in any given observation. So, since we are making assumptions about the error variance, so what does this error variance imply? That is, first of all, is explained here, that the deviations from the error term from its mean value could always be there, but then if there is no systematic pattern in it and we do not have any reason to anticipate a particularly erratic, or we anticipate a particularly erratic value in any given observation and we do not anticipate any systematic pattern, then we have heteroscedastic errors. To put it another way, the probability of u, the population error, reaching a given positive or negative value will be the same in all observations. When this condition is not fulfilled, we have the problem of heteroscedasticity or heteroscedastic error terms. So, we are basically focused here on the probability of u reaching a positive or negative value, that is u taking up a positive or negative value should be actually constant and there is no systematic pattern. Therefore, homoscedasticity fails whenever the variance of the unobservables change across different segments of the population, where the segments are determined by the different values of the explanatory variables. So, that is one possibility, that we have different segments, we can depending on the independent variable we have different segments of the dependent variable, and for different segments we have different error variation. So, then we can associate some non-constant probability in the dispersion of the population error from its mean term or mean value. Now, consider the multiple linear regression model, the standard multiple linear regression model, where we have k plus 1 variables. The homoscedasticity assumption played no role in showing whether OLS was unbiased or consistent. It is important to remember that heteroscedasticity does not cause bias or inconsistency in the OLS estimators of the beta j's. So, unbiasedness and consistency property remains even when the errors are not homoscedastic or the errors are heteroscedastic. The estimators of the variance of beta j hat are biased without the homoscedasticity assumption. So, the problem is that if we do not have homoscedasticity, then the estimators of the variances, that is variance of beta j hat, which we actually measure as sigma square x prime x inverse, just to recap, that is, these estimators are actually biased if the errors are heteroscedastic. Since the OLS standard errors are based directly on these variances, they are no longer valid for construction of confidence intervals and t statistics. So, this is the error variance. Now, this when we have heteroscedasticity, this error variance is no more sigma square, it is something else. We can call it sigma square I, that is, it is actually varying from observations to observations. and the standard error of the estimated parameters, that is standard error of beta j hat, is basically root over variance of beta j hat, right. Now, what is happening is that since we do not have homoscedastic errors or we have heteroscedastic errors, so that is why the standard errors are no longer valid for constructing confidence intervals and t statistics. They are not valid for other statistics also, if we talk about F statistics or F tests conducted in order to test for joint significance of several hypotheses. We have not talked about F test at length as of now, that is why I would not spend or talk much about F test right here. In summary, the statistics we use to test hypotheses under the Gauss-Markov assumptions are not valid in the presence of heteroscedasticity. So, the Gauss-Markov assumptions that we considered, there were 5 assumptions, one of them was the assumption of homoscedasticity. So, in presence of heteroscedasticity, that assumption is actually not fulfilled. Formally, heteroscedasticity is defined as variance of u given x is not equal to sigma square, rather it can be defined as sigma I square, where variance of u I conditional upon the values of x. In the presence of heteroscedastic errors, the problems that arise are, first of all, variance of beta j hat is biased, which I have just mentioned, that is variance of beta j hat is not equal to sigma square x prime x inverse. Therefore, they are no longer valid for construction of t statistic and F statistic, as they do not follow t distribution and F distribution anymore respectively in the presence of heteroscedasticity. And the second thing is that the estimated parameters, that is beta j hat, is no more blue, that is best linear unbiased estimators. So, they are still linear, they could be still linear, they are still unbiased, but they are not best, that is they are not the most efficient estimators anymore. So, it is no longer the most efficient estimators in its class. So, the property of OLS, that is OLS estimators are blue, is violated in the presence of heteroscedasticity. Now, we graphically illustrate heteroscedasticity. So, the presence of heteroscedasticity can be also observed or detected through graphical presentation. We present here a typical scatter diagram between x and y. So, we have y is measured on the vertical axis, x is measured on the horizontal axis, and if y were an increasing function of x, so given the line plotted between x and y, it shows that y is an increasing function of x, which implies that as x increases, y also increases, right. We see that although the observations are not necessarily farther away from the non-stochastic component of the relationship represented by the line y equals beta 1 plus beta 2 x, there is a tendency for their dispersion to increase as x increases. So, this is my line, which is the non-stochastic component. If you remember, initially I had mentioned that y equals to alpha plus beta x plus u can be divided or decomposed into two components. This component is called the stochastic component, that is the random term, and this is a non-stochastic component, right. Or essentially what we are trying to do is that by through all these estimation processes, we are trying to estimate this non-stochastic component. Okay. So, this is my non-stochastic component, which is y equals alpha beta 1 plus beta 2 x or alpha plus beta x, whatever you call it. And what we observe the presence of heteroscedasticity, we can see that as x increases, y also increases, but the dispersions are increasing. So, if I draw lines measuring the dispersions, then you can see that the dispersions are increasing, specifically they are higher during this range, which may indicate that at least the variance is not constant. The error variances or the differences between the plotted line and the actual value. So, that is the error term. Their differences or their deviations from the mean is actually not constant over time or may not be constant over time, or the probability of the deviation from the mean value is not same. for all observations. So, this is how we can observe heteroscedasticity. Another illustration is like when we are plotting the estimated residuals, that is the sample counter part of the population error terms. We have residuals plotted against one of the independent variables, say x 2, in case we have a multiple regression analysis and we have more than one independent variable. So, x 2 is one independent variable and u hat is plotted against them. So, suppose a regression has been estimated and the residuals u hat are plotted against one of the independent variable x 2 as shown in the graph. It is clearly evident that the errors are heteroscedastic, that is, although their mean value is roughly constant, their variance is increasing systematically with x 2. Suppose this is the mean. If this is 0, then you can understand that the positive value and the negative value roughly cancel out with each other, as a result of which the mean of this residual term u hat is equals to 0. So, if this is the mean of u hat, the deviation of u hat from its mean value is systematically increasing as the value of x 2 increases. So, this is a very clear cut pattern of the presence of heteroscedasticity. But graphical inspection of heteroscedasticity is not advisable. So, when we try to detect the presence of heteroscedasticity, graphical inspection is not advisable, because if we plot u hat against another independent variable, say x 3, we may not observe any heteroscedastic pattern. So, we have to individually plot the residuals against each and every independent variables, and then some of may turn up or show up some kind of a typical pattern in the movements or in the dispersion of the error term or the residual terms from its mean. Further, the error variance may change over time instead of changing with any particular independent variable. So, with any independent variable we may not observe any typical pattern, but the error variances are increasing over time. So, this is a special kind of case which is often handled in time series analysis specifically, but also applicable in the context of cross sectional data, and they are called autoregressive conditional heteroscedasticity, and this kind of models we will be dealing with in later modules. So, there are a number of formal statistical tests for heteroscedasticity, and we will discuss 4 such tests here, namely the Spearman rank correlation test, the Goldfeld quant test which was suggested by Goldfeld in 1965, the Brosh-Pagan test and the White's test. Right, these are the 4 alternative tests which we are going to discuss here. So, we begin with Spearman rank correlation test. The Spearman rank correlation test assumes that the variance of the disturbance term is either increasing or decreasing as x increases. So, there is a clear cut pattern either increasing or decreasing between x and the residuals, and therefore, there will be a correlation between the absolute size of the residuals, that is absolute value or mod value of u hat, and the size of x in an OLS regression. The data on x and the absolute values of the residuals are both ranked, and the rank correlation coefficient is calculated as this. So, this is denoted by r x u hat, which is equal to 1 minus sigma summation I equals 1 to n d I square divided by n into n square minus 1, where d I is the difference between the rank of x and the rank of u hat for the ith observation. I will explain the procedure using an example, but before that let me tell you that under the assumption that the population correlation coefficient is 0, the rank correlation coefficient has a normal distribution with 0 mean and variance 1 upon n minus 1 in large samples. The appropriate test statistic is therefore r x u hat root over n minus 1. Okay. So, what it says is that r x u hat follows a normal distribution with mean 0 and variance 1 upon n minus 1, right. Then what would be the standard normal distribution? The standard normal distribution would be r x u hat minus 0, which remains 0, divided by root over 1 upon n minus 1, as a result of which this is r x u hat into root over n minus 1, and this is essentially the test statistic that we would go for in case we are going for a t-test, or if we are going to check it against standard normal distribution. In both cases this is my test statistic, and the null hypothesis of homoscedasticity will be rejected at the 5% or 1% level if its absolute value is greater than 1.96 or 2.58, which corresponds to the 1% level, using a two-tailed test following the standard normal distribution. If there is more than one explanatory variable in the model, the test may be performed with any one of them. So, there is certainly some randomness involved in it, that which variable you are going to pick up, or you may consider all the possible variables alternatively, that is one by one. Now, this is an example where we are considering GDP values or GDP figures of 28 countries. So, we are running a regression, OLS regression of manufacturing output on GDP for a set of 28 countries, and this yields the following results. So, we have y hat equals 604 plus 0.194 x with an r square of 0.89. So, this is a cross country analysis. This implies that manufacturing accounts for $194,000 for every $1 million increase in GDP in the cross section. The residuals from the regression and GDP are both ranked as shown in the table. So, GDP is the only independent variable we have considered from the analysis. It is first ranked from 1 to 27, and then the corresponding residuals are also ranked. So, the first country having a rank with respect to GDP as 1, in terms of residuals it has a rank of 2 and things like that. Okay. So, when these are ranked, then I calculate DI as the difference between rank 1, rank of GDP minus rank of residuals. So, this is minus 1 here, similarly 2 minus 4 is minus 2, 3 minus 8 is minus 5 and so on. And then I consider DI square. So, minus 1 square 1, minus 2 square 4 and so on. The sum of DI square turns out to be 1608. Therefore, the rank correlation coefficient is calculated as 1 minus 6 into summation DI square is 1608, and then n into n square minus 1, which is 28 multiplied by 783. This gives us a value of 0.56. So, the test statistic will be the rank correlation coefficient 0.56 multiplied by root over n minus 1. There are 28 countries. So, root over n minus 1 is root over 27 and we get a value of 2.91. This is above 2.58 and hence the null hypothesis of homoscedasticity is rejected at the 1% level, and when it is rejected at the 1% level, it is obvious that it will be rejected also at 5% level. So, the null hypothesis is rejected here. Is essentially, if you remember, this is our distribution, and probably here I have 1%. So, this is 0.05%, this is a two-tailed test. So, 0.005%, and this corresponds to 2.58 minus, here it is 2.58, and 2.91 lies here, as a result of which it does not fall into the acceptance region, it falls into the rejection region. We reject the null hypothesis. Now, we talk about Goldfeld-Quant test. One of the simplest method is this Goldfeld-Quant test. The steps involved in GQ tests are, first of all, split the sample into two subsamples of length n1 and n2. It is not necessary that n1 has to be equal to n2. So, n1 equal to n2 is not necessary. We can have n1 not equal to n2, we also can have n1 equals to n2. The regression model is estimated on each subsample and the two residual variances are calculated as sigma 1 square and sigma 2 square. So, you can see that sigma 1 square is u1 hat prime u1 divided by n1 minus k, similarly u2 hat prime u2 divided by n2 minus k respectively. The null hypothesis is that the variances of the disturbances are equal, which can be written as sigma 1 square equals to sigma 2 square against a two-sided alternative. So, the null hypothesis actually talks about the two variances. If the two subsamples have the same variance, then it means there is no heteroscedasticity. The variances are same across all the observations. The test statistic is GQ is denoted by GQ following Goldfeld and Quant, is written as sigma 1 hat square divided by sigma 2 hat square, where the larger of the two variances must be denoted by sigma 1 hat square or it should be in the numerator. Now, this may correspond to any one of the samples. Of course, here one refers to the first sample, but the point is that the larger variance must be in the numerator. We can conduct an F test to test for the significance of the test statistic, and the null of a constant variance is rejected if the test statistic exceeds the critical value. The GQ test is simple to construct, but its conclusion may be contingent upon a particular and probably arbitrary choice of where to split the sample. Suppose that it is thought that the variance of the disturbance is related to some observable variable z, which may or may not be one of the regressors. A better way to perform the test would be to order the sample according to the values of z or z, and then to split the reordered sample into n1 and n2 observations. So, this just provides some guidelines about how to go for a split, but then there is no specific rule about how to split observations or the sample. So, that is one problem with the GQ test. Now, if we continue with the previous example, then we see that with using the same data used for Spearman's rank correlation coefficient, like the first sample we split the sample into two subsamples and we actually leave some of the observations from the middle part. So, that is also one solution in order to tackle heteroscedasticity. So, instead of 28 countries, let us take 11 plus 11, 22 countries. So, we consider 11 countries with the largest GDP and 11 countries with the smallest GDP. We could have worked also with 14 countries with the largest GDP and 14 countries with the smallest GDP. The RSS from the two regressors are observed to be 13518 multiplied by 10 raised to the power 6 and 157 multiplied by 10 raised to the power 6 respectively. Note that since n1 is equal to n2, we need not calculate the residual variance, because residual variances are simply RSS divided by n1 minus k, RSS divided by n2 minus k. So, what we simply do is that go for RSS 1 divided by RSS 2, because in both cases we have n1 minus k and n2 minus k in the denominators, and since they are the same value, so they cancel out, and we observe a GQ value of 86.1. The critical values of the F statistic or the corresponding F statistic with the degrees of freedom equal to 9 is 10.1 at 1% significance level. Therefore, the null hypothesis of homoscedasticity is here also rejected, right, because the critical value or this value of the statistic calculated is much higher than the critical value. Now, we talk about the third test, that is the Brosh-Pagan test. Here we consider the model y equals a multiple regression model, y equals beta naught plus beta 1 x 1 up to beta k x k plus u, which is our original model or model of the world. We assume that expected value of u given x is equals to 0. So, the mean value of the sample residuals are also expected to be 0. Therefore, beta hat OLS is consistent and unbiased, no problem, and we want to test whether expected value of u square given x or conditional upon x equals to expected value of u square equals to sigma square. This is our null hypothesis against an alternative hypothesis that variance of u conditional upon x is actually not equal to sigma square. If h naught is false, then expected value of u square conditional upon x can be any function of the xi's. A simple approach is to assume a linear function. So, we assume a linear function between u square and the values of x, right. The null hypothesis of homoscedasticity implies that all these coefficients are going to be 0. So, if all these coefficients are equal to 0, then this implies that u square is not dependent on any of the independent variable, at least linearly. Under the null, we assume that covariance x and v is equals to 0. Therefore, the null hypothesis can be tested using an F test. In order to test the null hypothesis, we consider OLS estimates of the U from equation 1 and run the regression of equation 2. So, this is the first regression that we run, obtain the corresponding values as U hat, and then we run this regression with U hat replaced by U hat square, and we already have values of x1 to xk. The null can be tested using an F test with k n minus k minus 1 degrees of freedom. The LM version of this test is called basically the Breusch-Pagan test or BP test for heteroscedasticity. The steps of BP tests are: first of all, estimate equation 1 and collect U hat. Second, run the regression in equation 2 and keep the R square, which we called R square U hat. This is because this is not the R square generated from equation 1, rather it is generated from equation 2, where the independent variable is U hat square, and that is why we call it R U hat square. Form the LM statistic, which is n into R U hat square. So, the sample observations or the number of observations in the sample multiplied by the R square obtained from regression 2, and this follows a chi-square distribution with k degrees of freedom. So, again depending on the value of the statistic and the critical values given by the chi-square test, we may reject or accept the null hypothesis or not reject the null hypothesis. And the last test that we discussed is that of White's. A further popular test is White's test, which was given by White's in 1980, which is a general test for heteroscedasticity. The test is particularly useful because it makes few assumptions about the likely form of heteroscedasticity. So, unlike Breusch-Pagan test, it actually does not consider only a linear combination of the independent variables or U hat square as a function of the linear combination of the independent variables. It tests whether variance of U is uncorrelated with all the independent variables, their squares and their cross products. Suppose k is equals to 3, that is there are only 3 independent variables x1, x2, x3. Then White's test is based on estimation of U hat square on x1, x2 to x3, and then x1 square, x2 square, x3 square, and then cross multiplication of x1, x2, x2, x3, x1, x3, right. We can also add terms like delta 10, which is multiplication of x1, x2 and x3, all 3 are multiplied together. And then we go for the null hypothesis, which is delta 1 to delta 9 all are equal to 0, is testing using an LM statistic with 9 degrees of freedom, and F test can also be performed in this context. The weakness of White's test is that the number of regressors and degrees of freedom multiplies with increase in the number of regressors. So, when we have k plus 1 regressors, White's test will have 2k multiplied by k into k minus 1 divided by 2 restrictions. So, that is a large number of restrictions. An alternative testing procedure is to consider y hat. This is very similar to the Hausmann specification test, endogeneity test that we discussed under omitted variable problem, that we go for, we actually obtain y hat as estimated values obtained from a regression of y on x1 to xk, and test for heteroscedasticity by estimating the equation where U hat square is a function of y hat, which actually includes all the independent variables, and then y hat square plus an error term. Here the null is delta 1 equals to delta 2 equals to 0, and this can also be tested using a LM or F test statistic. So, these are the references that I have considered in order to come up with the discussion on definition of heteroscedasticity and detection of heteroscedasticity, what kind of problems it causes to the OLS estimates, and in the next module, that is module 18, I am going to deal with how to deal with heteroscedasticity, that is if there is heteroscedastic errors, then how we can still get other minimum variance estimates of the OLS regressors. Thank you.